Okay, I'm going to do a little reshoot of a video that I made some time ago. Unfortunately, I think it got lost or something messed up happened with it. But basically, this is going to be some important stuff about the Hydrautomat, and kind of stems from some things I overlooked about these traps, that they can actually be used as check valves if you proportion them properly in respect to the distance between the operating tank and the ground here, or at least where the siphon ends. So I'm going to, I don't know, probably start with the basic intro to Pascal's law first, and then just go through the whole thing here. So that's what I'm going to get to doing. Okay, so first, this whole thing basically stems from Pascal's law, which is the pressure at any given point is equal to the external pressure being put upon it, plus the density, which is what this rho symbol here is. Okay, should probably hold it up closer to the camera in case YouTube doesn't have as high quality or something. So as P external, the pressure external, plus the density of the water, because that's what our material is, in this case is water. Air you really don't have to consider, so don't even worry about that. Multiplied by the force of gravity, or G, and then times the distance in height between, whatever given point. So all you need to know is that's kind of where this whole thing stems from. You can look deeper into it, whatever. Basically, in this example, this camera has the worst time trying to focus, I swear. But anyways, what I did is I just turned these things into dP and dN. I guess N is for internal and dP is like pressure or something like that. But basically, I just decided to abbreviate it to make it easier to write things in. So here's a set of inequalities that you have to follow. Okay, so dP. Oh, I see why. Yeah, dP is the external pressure, or in other words, the pressure coming from this operating tank here. Okay, so the pressure that's generated inside the operating tank, whether it's pulling or pushing, alright, is being shoved up through this air tube into these two closed containers, and that's what your dP is, right? And that dP comes from the distance from the operating tank to the the vertical distance between the operating tank's water line, where the water is inside of it, to all the way down to the end of the siphon. So the amount of suction is determined by the distance between the water level and the operating tank down to the end of the siphon. So that vertical distance determines your suction pressure, or your negative pressure. Right, so that's what your these green D's are right here. That's all the same one thing. And so what I have here is function and backflow. So this is what you need in order for the thing to actually work, so it doesn't stall. And the second one is what you need for the backflow prevention, so it doesn't, so the water doesn't flow back the opposite direction on the other cycle. Because you only want the water to go up. You don't want it to get pushed back down into the lower containers. So that's the inequality you need for this one here. Thank you, camera. So that's what you need there. All right. And now I'll go into detail about the suction cycle here. Okay, so here's the page for the suction cycle, which you've seen before. And basically, as I said before with the inequalities, you need one set here, which is the blue versus the green ones, okay, in order for the thing to work, and the other one is to keep it from flowing in the other direction. Now, what I mean by that is, in order for this thing to work, you need these two, D1, D2 here, to be less than the, basically the pressure generated by these vertical columns. You see these blue tubes here? Those are the intakes, right? So in other words, the back pressure, the pressure from these tubes here, from the end of the tube, all the way down to the water line of the container that's filling into it, right? Because the feed tank would feed or fill the water inside this closed tank here. You need that pressure, okay? You need that length. Basically you just need the length to be longer than the length of this guy right here, right? You need to be less than that, because you need the pressure here to overcome the back pressure in here. So, because if there's not enough pressure in this operating tank, right, when it's pulling down, there's not enough negative pressure here. That back pressure, which is fighting against the feed tank, is going to keep that water from coming up into this closed tank here. You know, it won't have enough power to push this water in this feed tank. Anyways, it won't have enough pressure to pull the water from this feed tank up through that tube and into the closed container. So that's why you need more negative pressure on the suction cycle than what problems you'll get from that vertical distance between the water line of the feed tank to the water line, or actually rather just that tube there at the top of the closed container here. So I guess to recap it, this right here needs to be, this distance needs to be larger than the distance between your feeding container and the between your input container and your output container. So if the water is going from here to here, that distance needs to be less than the distance here. And of course, do remember that on suction only, you have to watch out for degassing, because after I think 32, 33 feet or 10 meters or whatever, what will happen is the suction will become so great inside this tube here that the air is actually going to separate out from the water if this water hasn't been degassed, which you're going to be using this outdoors, so unless you run a degasser first before putting it into your feed tank, there's going to be a whole bunch of air that's going to show up in this tube, and it's going to kill your siphon. So you do have a limit for your suction cycle, but pressure cycle you don't. Or if you want to run a degasser through, then you also won't have that problem. But I mean, degassing costs money, you know. Just look up degassing, and that's the whole process. Anyways, okay, so I'm going to go through the backflow part of this thing. So for the suction cycle, you can see this, the distance 3 and distance 4 that are marked in red here have to be greater than the distance for the water line in the operating tank down to the end of the siphon. So that distance there has to be less than these two distances here. And the reason being is that when this operating tank is draining out, which it does during the suction cycle, you do not want that distance to be greater. You don't want this one to be greater than this distance here. Or the same goes for this one as well. Because, you know, the two tanks here, this tank and this tank, are the same thing as this tank and this tank. This is just a repetition of this setup here. You know, fundamentally, you only need like this open tank and this closed tank, and then your feed and operating tank. This is just an extra stage. You know, these two last tanks are just an extra stage or phase, what do you want to call it. So anyways, when this thing's draining out, what will happen is since the pressures, you know, negative pressure or suction is determined by that distance, if that suction is more than the pressure that is generated by the height of the water in that tube that's marked in red here, alright, that's what your back pressure is determined by, is that distance, and that's what's fighting the air from the air that's trying to come from the outside down into this tube and up into the closed tank here. Because when this thing's pulling, what will happen is it'll pull on the water in this tank here through that blue tube, but it'll also pull through the red tube. And since the red tube is directly exposed to the air, it'll pull that, you know, that negative pressure will be pulling that water up into here, and you'll have a little air bubble. Well, the air will start to fill up this tube from the top down, and if it's too much, what will happen is it'll go past that U and it'll fill this thing up and it'll become a living nightmare, believe me. It's not fun to deal with that. So it'll screw up your system. You don't want that air to get into here. So that's why you want this back pressure here, which is the only thing that's fighting this thing right here. This is the only, that red part is the only thing that's resisting the air from being pulled up into that container. So that's why you want the kind of the output tube here, and these two red output tubes, I guess you can call them output tubes, you want those to be larger. You want them to be taller vertically than the height that DP is at or could become. Because do remember that the highest distance that DP can theoretically become is as high as this water line in your feed tank. Okay, because if you opened up like this tube right here and let this thing fill up, the water level will go as high as here. But because you have a seal technically with these two closed tanks, usually what happens is you get an equilibrium before the water can reach that level. So usually the operating tank will fill up somewhere in this section here between the top of that operating tank and the water line. It'll stabilize somewhere around here, depending on what your dimensions are. It's all pressures. Everything here is just relative pressures. So that's something you really want to make sure, is that the output tube, the length of that trap going downward, is larger than what this will be at, because this is what determines your suction, and that's what determines what fights that suction from pulling the air into the tank that you don't want it to be pulled into. So that's the other part here. Alright, so now I'm going to go to the pressure cycle. Okay, so now I'm going to go through the pressure cycle here, and as you can see, I should have colored this differently. Let me focus this again. I'm just having issues. I don't know. But anyways, as you can see, these are red and these are blue, so they're switched around. But they actually mean the same. They actually mean the same thing as the other colors. Sorry, what I mean by that is this right here determines the function, and this right here determines the back pressure prevention. I guess I decided to keep blue for the intake tubes and the red for the outtake ones, for the output ones. Keeping the same convention as the previous sheet. But anyways, so your pressure in this case, your DP, the variable here that's in green, your pressure is determined by the distance between the bottom of that operating tank and the water line here in the feed tank. So the pressure, from the top of that, from the water here going down, through the screen tube here into this operating tank, that's what determines how much air pressure. It determines the pressure of the air going up into this tube here. And the reason why I started it here at the bottom of the operating tank rather than, somewhere around here, is because, as you can see, this trap goes the other way back around. So Archimedes' principle basically states that this would be basically a communicating vessel. I'm not stating it exactly right, but basically the pressure from this point here, from the bottom of the operating tank down to that trap on this side, will cancel out the pressures on this side. So basically the pressures that you have left are determined by the bottom of this operating tank going to this water line. That distance is the only thing that's generating pressure, because otherwise everything below here is being nullified. So anyway, that's your D, maximum. Alright, it's kind of it's much more constrained than where this one is here, because suction changes as the water line changes, I think, and also the back pressure here. But this is basically your maximum distance here. So anyways, your function, in order for this thing to work, is actually determined by these output tubes now. Okay, so as you can see, they have to be less than the distance or the pressure generated from the operating tank, of course. So in other words, the back pressures generated from these red sections here have to be less than the green one here. And the reason being is that as the pressure is pushing up into these two closed tanks, which are now shaded, which is basically to show that they're filled with water, this tank here and this tank here. When the air is being pushed up into those tanks, it's pushing the water down and out and up into those tubes that have the red markings on them. Let me show you. So the water is being pushed up that red tube, and basically your back pressure, the resistance against that water, is going to start where that water line is, and it's going to end at the end of that tube. So the distance between here and here, going all the way down to the bottom of the tank, which is why I have the red ending there. So that's going to be your maximum back pressure. That maximum back pressure always has to be less than the pressure in this that's generated by here. Otherwise, like before, it's just going to stall out. The pressure here is going to be too high for the water to be pushed up past it, and past that pipe and into the open containers here, this reservoir and this other open container here. So anyways, the D3 and 4, okay, for these input tubes, those have to be greater. Those distances need to be greater to prevent the pressure in the operating tank from pushing air the wrong way, basically. So in this case, the air is actually coming from the operating tank, right? The air that you want to prevent is coming from the operating tank. So the air being pushed into this tube here, if there's too much, of course, the first place it's going to go into as it's being pushed down past that bottom there. If you have so much pressure, it's going to go down, and the first place it's going to loop through. I mean, if you have an incredible amount of pressure, it'll go into this tube as well. But you don't want it to get to that point first off. You don't even need to get here. So anyways, the air pressure will be pushed down the tube here on right next to my thumb, the output tube. Alright, and you want to make sure that that air does not get past that U, doesn't get past that trap. Otherwise it'll bubble out and into the atmosphere, and you don't have that air pocket anymore, and you have to like regenerate it somehow. So you have to open something up and let the air back in. Otherwise your system is limited, because there's more water, I wouldn't say in proportion to, but you need a certain amount of air in here to be able to push all the water out of those tanks and into these two open tanks. So that's a problem if the air gets past those U's. So basically the only thing that's fighting that pressure, that positive pressure in this case, from pushing the air all the way up into this tank here, and from this tank all the way up into here, because the air is going from this tank up into here as well. The only thing that's fighting that are what you see marked in blue. Yeah, I apologize for that. I kind of messed myself up here a little bit. I should have put these blue markings on the opposite side. But anyways, in order to keep the air from being pushed or whatever, to be pushed down, like say this tube here into the feed tank, or to keep the air in this tank here from being pushed down into this tank, basically the back pressures are generated by the water line all the way down to that trap, as usual. And I decided to put the markings on the opposite side, even though the pressure is coming from this side, from the side of this tank, and not from here. So this blue marking should be on the other side, but I don't know, I just did it at the time. So anyways, from this point here to this point here, that distance needs to be greater than, this distance. So in other words, you want to have that back pressure generated here be greater than the pressure that this would have here to drive air down that tube. So you want the water pressure to be higher than the air pressure for this vessel, pushing that, going this way. Otherwise the air can be pushed in that little tube there sticking up out of the top of this container, and it can be pushed down past that blue section there and bubble up into here, and that's just not going to be a good day. Same thing for this guy, for this pair. And in this case I did put the blue on the other side because the pressure is being generated from the water line in the feed tank going down to the bottom of the trap. So, that's your back pressure. That's what pushes the water up through this tube and up to this point. So when there's air being pushed out through here, you want to make sure the air can't get pushed past, this trap here. Although, then again, you also want to make sure the air doesn't get past this trap as well, because it'll just bubble up through here. The same goes for the opposite as well. So there's another set of inequalities for this pressure cycle. There probably might be one for the suction cycle too, I'm not sure. So for anybody interested in either designing the Hydrautomat, or you're at least curious as to how this thing works and why it doesn't need check valves for these tubes, because I remember, if you look at my previous videos, I also mistakenly believed that somehow, some way there needed to be check valves on this device. But because of the proportionality of those traps in relation to the distances between the feed tank, the operating tank, and the end of that siphon, because everything here is in the right set of proportions, you actually don't need check valves, which is really cool with this setup here. So as long as you have that worked out, as long as you keep these inequalities, all these proportions, as long as all this stuff holds true, as long as this is done properly, you won't have to use any check valves in your setup. You just need the containers and the tubing. And of course to have an air or watertight seal throughout this whole network. Preferably an airtight seal along the whole thing, not just where the air is going to contact, because you never know where the air is going to get to. But yeah, so as long as you have that set up, you won't need check valves, and it'll be easier to design and build. So yeah, definitely hope this little video helps anybody that wants to design this thing, and if anybody's curious about it, yeah, it's a lot easier to create than you would think. So thanks for watching, and definitely share and like, because that definitely helps this video get out to those who need it, especially those that need this kind of thing for bringing water long distances to like remote places in say Kenya or Uganda, even in India. There's not, electrical power is not readily available, so definitely share this out to people that can make a difference in those areas. And yeah, thanks for watching.